So we begin chapter 5, discrete random variables. So in chapter 5, we're going to take these ideas of probability we did in chapter 4 and start marrying them to the ideas of descriptive statistics we looked at chapters 2 and 3 and get us towards inferential statistics, which it's our main goal where we're acting at. So today we're going to do on this lesson, a lot of defining. So we're going to define what we mean by a discrete random variable, what do we mean by a probability distribution, and then we will construct probability distributions. So we'll start off with a good descriptive statistics idea here. Diego sent out a survey, sampled 50 subjects, asked how many siblings do you have, got this frequency distribution. So looking at this, we say 36% of the students he surveyed had 2 siblings. So this idea, number of siblings, what does this have to do with randomness? What do you think? The number of siblings is a variable, because the number of siblings is what changes. You ask somebody how many siblings you have, you don't know what the answer is going to be. The number of siblings you get as your variable x, your answer is going to depend on who you picked, and that's where that uncertainty, lies, where that probability comes in, where that randomness comes in. So we call the number of siblings our random variable, because it is the thing that's changing, but its value depends not on some function, but it depends on random chance. So that's what our definition. A random variable is quantitative. A quantitative variable whose value depends on chance. A discrete random variable is a random variable whose possible values can be listed. There's a finite number of possible values. It's discrete. In this past case, you can't have, you can have 1 siblings, 2 siblings. You can't have 1.5, 1 3/4. And although theoretically that could go to infinity, realistically, there's a finite number of possible values for that. So notation we're going to use. So when we're doing variables, we normally use like x, y, and z. For random variables, we're going to use uppercase letters. So in this case, when we look at this, the event that the student has 3 siblings, we would say capital X as our random variable equals 3. So the probability of X equals 3 is the way we're going to denote this. So if you notice the relative frequency, we say how often does this happen? This meshes really well with our ideas of probability. We had 50, the frequency over the number. That's how we found relative frequency. That's how we found probability. When we have a discrete finite variable, relative frequencies are the same as the probability of our random sample or random variable. So that's nice. That kind of helps us. We already know how to do this. Yay! Okay, right. Listing of possible values. Your distribution, again, all of the possible values of the random variable and the probabilities. The graph, the histogram is the graph of the probability distribution. And when we do this, we will always have the variables of the discrete random variables on the horizontal axis. Probability is on the vertical axis. So we will always make these vertical histograms. So coming back to this data here, we're going to start all over again. The probability distribution of the random variable x and make a probability histogram. So I'm going to give you a whole bunch of stuff, and it's going to say, hey, we already did this, because we already did. There's that connection between the relative frequency and the probability of the random variable. So again, the probability of x equals 3 is how many times does x equal 3? How many times total? So we have 10 over 50 is 0.2. We do this with all the rest of them. You notice we got the exact same values here? Because it's the same thing when this is a discrete random variable. So here's our histogram. I just want to show you this on decimals. This might be worth noting. We didn't really do much when we talked about graphs at that time. So let's switch over to decimals here. To get this, I'm going to start from scratch. If you bring up the show your keypad under functions, if you click on, we got all sorts of stuff under here. But under distributions, notice we have a histogram, a dot plot, and a box plot. These distributions we will use when we get towards the end of the semester, but right now we're going to go with the histogram. Now the histogram wants the data set and the bin width. Now the data set, you have to start with square brackets. I'm going to get this out. And we just start typing our numbers separated by commas. But the thing is, I don't want that, comma. Close this here. Oops, I have a comma. So notice for this, it's an error. We need something on both sides of the comma. Oh, duh. 2. Whoops. Now you can give your bar height as a count or relative. When we're doing probability distributions, we're always doing the relative. Density, we're not going to mess with right now. We can do bin alignment center or left. And remember, when we're doing a histogram, if we are doing discrete data, we're doing single value grouping, then we're going to do center bin alignment, where the number is right in the middle there. If we are doing a bin width other than 1, then we would say, so if I want a bin width of 2, then I would go left. So here's 2, 4, 6. If you remember that. But for these probability distributions, we're dealing with discrete random variables. We'll always do this center line here. When we look at this one here, to do the data, unfortunately here, I had 3 zeros. 3 people said 0, so I had to type in 0 3 times. I had to type in all of the ones. I have to have all of the data here to use decimals to do it. Now, if you have your data in a spreadsheet, you can copy a column from the spreadsheet, paste it in where it says histogram, and it will column delineate and put it in here. You just have to put the square brackets around it. So you can play with this when you're making your frequency or your probability histograms. So just a little side note to explore. This might be useful to you. Let's go back to here. Let's go back to full screen. So the number of siblings is a variable of a finite population. And again, because it is a finite, discrete finite variable, the relative frequency distribution and the probabilities are the same. Also notice the probabilities sum up to 1, which is a good double check here. You notice when we add all our probabilities, we get 1. That should happen. If it doesn't, there's something else going on. Let's get my little bar to disappear again. So our official definition here, sum of the probabilities of a discrete random variable. And we do that with the, okay, go away again, blah, 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 blah. You notice we have the capital X. Every time I move the mouse, it does that. Oh, and it gives me even more. Sorry about this. We use the capital X for the discrete random variable and the lowercase x for the value we're looking for. So this is saying the sum of all of, we're summing up as the random variable equals every single possible value it can be. We add all of those sums, those probabilities up, we should get 1, which is just make your table, sum it up, so all the probabilities should add to 1. So I'm going to give you a chance to try one of these problems and we'll work through it together. Balanced coin is tossed 4 times. We have 16 possible outcomes. I've made your sample space for you to make this a little easier. There are 16 possible outcomes. So if X is going to be the total number of heads, X could be 0, 1, 2, 3, 4. This is a discrete random variable. It is discrete. We got 5 possibilities and only 5. We can list them all. So I want you to find the probability that X equals 2 and explain its meaning. Find the probability distribution of X. And then use this notation to represent the event that at least 2 heads are tossed. And then find the probability. So pause the video, work through this, see what you can get, and then start this back up again, and we'll walk through this with you. So P X equals 2 means we're looking for the probability that there are exactly 2 heads showing when the coin is tossed. We look through, we have 6 possibilities out of 16 that have exactly 2 heads. So my probability that heads comes up exactly twice is 0.375. So to find the probability distribution, this is pretty much the same again as doing the relative frequency distribution. We would start off with my value of X is the number of heads I flip. So I can get 0, 1, 2, 3, or 4. And I find the frequency of each one. This I have the sample space, I can just count them out. Then to find the probability that X equals X is the frequency divided by the total. Gives me my frequencies here. And notice they do sum up to 1. And they should be. We want to do that as a double check to make sure we've done this correctly. Now, you might be off just a little bit again because of rounding errors. In this case, there aren't any, so that works out nicely. But keep that in mind when you look through this. So, random variable notation to represent the event of at least 2 heads tossed. That's going to be this. We want X is greater than or equal to 2. And X is greater than or equal to 2 means X equals 2 or X equals 3 or X equals 4. Now we can look at and think back to what we were doing before. These are mutually exclusive events. When we're doing or, we're saying if we're mutually exclusive, that means we can just add the individual probabilities to find this probability. I mean to say, okay, this is wrong. They're not mutually independent. They're mutually exclusive. Let me fix this. I'll refix this on the slideshow. Get out to my tablet so I can write on this. Oops. As I say, I don't want to re-record the whole video, but I will correct the slideshow. Mutually exclusive. So we can take the individual probabilities, add them together, and the probability that you will toss at least 2 heads is 0.6875. So, enjoy.